All right, so this week we are diving into the wonderful world of Modbus. And just like last week and the week before that, we're going to start with a lovely video from Real Parse. Is on D2L if you want to go watch it. And if not, you can go find it on the internet. All right, real quick, since it's on the screen, what's the difference between Profinet and Profibus? Fine interface. Ports, again, go more on ports. Go ahead. Excellent. Profinet is overall Ethernet based. It's not truly Ethernet, right? It's kind of a variation, but it's mostly Ethernet. Profibus is RS-45, 485 based, all right, which is kind of a variant of RS-232 that we talked about in the very beginning of the class. So it's still serial, but now we've got differential signaling and things like that. So same underlying protocol, it's just how we're transmitting the data from point A to point B. Is it over two pairs or two wires, two twisted pair wire? Or is it over an Ethernet cable? That's really the whole difference, as far as I'm concerned, for Profinet versus Profibus. All right, so in quick overview, master-slave. That's what we've got going on here again. Again, if you don't like the term master-slave, there are tons of other ones. I'm sorry. It's just this is the one that's ingrained in my brain. So it's what I'm going to keep using, and even though it's outdated now, but it's just what it is. All right, nice thing here is we have up to 247 slave devices. If you remember going back to Fieldbus that we just talked about last week, no, we talked about Profibus last week. FieldNet device, yeah, that was 2 weeks ago, which was kind of a combination of all these things are kind of fitting into that one. But Profibus wasn't that many. All right. So this one, we've got a lot of different options here when it comes to devices that we can have hooked up to the network. Big benefit here, it is an open protocol, which is very nice. All right. That means just like we did with the Profibus stuff last week, we could do this as a Arduino as the slave device. So you could go that route if you wanted to. Right? And there are libraries and things and lots of tutorials on the internet about doing that. I don't think we're going to go do that because it's basically the same lab we did last week. It's like, wire up this RS-485 adapter. And it's like, it's the same thing we just did. It's just a matter of sending the right protocols over that network. Right? Maybe next week I will get the oscilloscope out so we can see the signaling and those types of things if I'm lucky. I also might have another lab for us. That'll be hopefully kind of interesting. All right. So yeah, it is open. Application layer 7 again is kind of that top level layer is where we're changing things up a bit. It's really what it comes down to. And this is overall, as the video said, a modification of a traditional serial communication. Right? We're taking that RS-45 serial network and we're tweaking it to fit our needs, making it per se a little better. Maybe. All right, so as I said, I call it a master slave. If you want to call it client server, that's fine as well. All right. So we have, as the video again talked about, we have requests, confirmations, indications, and responses. All right. So this is kind of like can be a 4-step process per se, and more of like a 2. So Modbus, we have requests. This is the message that's sent on the network by the client to initiate the transaction. All right. I think this might be more the Ethernet-based one than the serial-based one, but we'll just go through this anyway. Then we have the confirmation, and this is the response message received on the client side. Then we have the indication. This is the request message received by the server side. And then we have the response, which is the message received sent by the servers. So it's kind of a back and forth little thing going on there. But here's where I really want to get into. Right. Modbus is hexadecimal based. Yay! All right. So this is 0 through F. So 0 through 9 and then A through F, as I am showing you up here. Yeah. All right. So that's what we've got going on there. It is 0 through F. All right. So this is base 16. So if you would count them all up, you would have 16 different possible combinations. Right? If you've never converted a hexadecimal number to a base 10 number, what we're used to, right? All right. If I have 2 slots here, and I say this is 11 is my number that I've told you it is. And if I didn't tell you this was hexadecimal, you guys would be like, the answer's 11, right? All right. But if I said, hey, this is hexadecimal, now you're all going, oh, damn. What does that now mean? Equal. All right. And simplest way is to write out overall. So this one is 16. All right. So we've got 16 there. This one would be your ones. So normally this would be 10s, right? We would say 10 times this number plus 1 times that number. Well, in this case, we're doing 16. So we have 16 times 1, so that'd be 16 plus 1 times 1 is 1. That'd be a decimal equivalent of a 17. Right. It's really not that difficult in the long run to go through and do these types of things. Right. Now, if we said this was an F, which would be 15, that was an F now. So 15 times 16. Anyone got the number off the top of their head? Yeah, I don't either. All right. So you've got 10 times 16 would be 116. 5 times 16 is 50, is 80. That'd be 240, right? And I think my math is there is correct. So that would be 240 plus 1, equals 241. So there you go. It's really not that difficult in the long run, as long as you just think about this as A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. My opinion, it's really not that bad. But anyway, so that's how you kind of roughly go about this. And then if we would go to this next spot here, it wouldn't be 17. I think that's 240, so that would be 250. I forget. I'd look up that one. I think that's 16 times 16, so that'd be 256. Makes sense. All right. So we're exponentially getting bigger and bigger and bigger each spot here. All right. So just kind of, again, something to keep in the back of your mind. It's a different system, but it isn't really that bad in the long run. All right. So hexadecimal is base 16. Binary is base what? 2. All right. Binary is base 2. All right. So the benefit to hexadecimal in the world of computers. Why does hexadecimal? Why would we ever want to go to the 16th? All right. And I will ask you the same question about time. Why would we stop at 60? Why are there 60 seconds in a minute? Why couldn't there be 100 seconds and 100 minutes in an hour? Why? It just doesn't make sense. We just have to make a second a little bit shorter, and we can go to 100 seconds in a minute, no problem. All right, but we don't. We have our time is base 60. That's really what it comes to. All right, let's take it to hours, and it's 24 hours. I'm like, it makes no sense. But anyway, the reason we like hexadecimal is it uses up all 4 digits or 4 bits of that binary number. All right. If we were going to only count to 9, like we do with our base 10 system here, you would see we could count to 8 or 7 with only using 3 bits. But once we go to 8, we now need 4 bits. And 9 is 4 bits. So we actually are not using all of the bits possible when we're using a base 10 system in a computer world. We're not using these 6. Not using those. They're wasted. Right? So when it comes to efficiency of computers, hexadecimal starts making more sense because we're utilizing every bit possible. Like, why is 1 megabit 1024 kilobits? Like 1 megabyte is 1024 megabit kilobits. Because again, we're using all of that information. Right? I think it's actually like a kibibyte. I don't quote me on that one. My computers are good but not great. Kibi, yeah.
Base 7.
Not that I know of. It technically should be actually probably base 8 because it's 0 still. But technically in my mind it should be a thing, but I don't think it actually is. But yeah, if you ever hear someone term like the kibibyte or gigi, I remember there's something with an I that when you throw it in there, it goes from it being 1024 to 1000 or something. It's a weird thing in the world of computers, and but it's something you have to deal with. So anyway, yeah. So I'll get you guys to take a minute or 2 or 3 or 5, a few minutes, and try to convert 18 to hexadecimal and AA to decimal. All right, so the 18 to hexadecimal. Okay, Dylan, what do you got? No. Okay. Anyone? Anyone else have a guess? No. All right, how about we start with the AA? Go ahead, take another minute. I showed you how to convert a hexadecimal to decimal already. That's why I want to start with that one. It's a little bit easier. All right, so we've got all of your guesses, and unluckily you all are way off. All right, which is fine. This is why we're going through this little activity here. All right, so I told you, right? Got little numbers here. We're going to put A there and then A here. And I told you that this is 16 and this is our 1. All right, so what's the value of an A? You had to put a specific decimal value to A, what would it be? 10, correct, right? It's after 9. So an A equals 10. All right, and then what I tell you to do? Multiply down, right? So it would be 10 times 16 is 160. 10 times 1 is 10. We add those together, equals 170. Not that difficult, right? When you think about it that way. It's just a matter of taking it step by step by step. And as I've told you guys before, on Windows, there is the programming calculator is absolutely wonderful. It's 5. All right, so if I click on decimal here, not decimal, I need to click on hexadecimal, and I type AA, boom, shoots out the answer for you right there. Right? This is one reason why I'm not like super focused on you better be able to translate these. Yeah, there's so many good systems out there that will convert stuff for you anymore. That I'm not saying it's not good knowledge to know how to do by hand, because maybe one day you're there and you're like, oh yeah, just get my phone out and do this, and you're like, I left my phone at home. And you're like, all right, how do I do this again by hand? All right, but it's still a good thing for you to have in your back pocket for a rainy day when something screws. That's how we would do that one. All right, now, you guys want to take a shot at the 18 to hexadecimal, or are we going to walk through it together? You're all acting like I'm nuts. All right, let's go ahead and get rid of all of our ink on this screen. All right, so we've got 18. Now, there's not as nice of a system here. Thank you. It's not as nice of a system to me. It's not like, oh yeah, just fill this in, you're done. All right, so what you have to figure out is, if we've got 3 spots here, right? This is our world of hexadecimal. And I told you this is 1, this is 16, and this is 256. All right. Is 18 bigger than 256? And we could keep going here, right? You know, if we did 256 times 16, that would be this one. And we did multiplied it by 16 again, it'd be that one. But is it, you have to find the one that is bigger than, but not a lot big, but really that's bigger than. So is it bigger than 256? No, so that would be a 0, right? Is it bigger than 16? Yes. All right. So 18. All right. If we divide that by 16, what do we get? Go ahead. 1.125. All right. So anytime you're dealing with these types of things, we have to ignore what I would call the remainder, right? We only care about integers. Yes, we're going back to the world of math here. Integers are whole digits. We can't have any decimals, right? Because we don't have a place for decimals in the system. Right? So we have to have whole digits. So 18 divided by 16 is 1.125. So you would put a 1 here. All right. Now, what's 0.125 times 16? Or what would be the remainder? If I said, okay, 18 divided by 16 gives me 1 whole, what's left? 2. All right, right? Because if I said, okay, I only get 1 whole 16 out of this. So if I say 18 minus 16, that equals 2. So then 2 would be what would go there. All right? Making sense? You're like, not a freaking chance. All right, so let's go through this again. Someone pick a number for me. Go ahead, just yell it out. 27. Okay. 27. Okay, 27 divided by 16. Again, I only care about whole digits here. 1 with a remainder. So we can just put a 1 here. So we would then do 27 minus 16 equals 11. Can we put 11 there? Yeah, that's 2 digits, right? So we couldn't put 11 there. So what would we put there instead? B. Because A would be 10, B would be 11, I would continue, C be 12, yada, yada, yada. So it'd be 1B. That is the equivalent of 17. All right, it's making a bit more sense. All right, so let's do one more time. Because, you know, it's fun, right? Y'all enjoying this. Let's go with like 99. Go there. I'll give you guys all a minute to try to do this on your own, since we've now done 2 nice examples. Go ahead, Dim. It'd be what, 6? Remainder of 1. You're saying 61. Yeah. That's not what I have. Close, but not. All right. So anyway, we haven't done a big number before, right? We've only done single. So I understand a little confusion. So we say 6. All right. So what's 6 times 16? 6 times 16 is 96. So we would do 99 minus 96, which equals 3. So it would be 63 would be the answer. All right. Close. As I said, right idea. You just screwing your math up. This is why calculators are great, right? When I used to teach math 99, now math 101 or something. I don't remember. I used to tell my students, I'm like, you are allowed to use calculators. Use a calculator. Like, yeah, use the tools that are provided. Again, I understand, you're not always going to have the tool, but have the tool, use the tool, especially when you're first learning it. So it's like, okay, let me make sure, double check yourself with the tool type of thing. Very easy to make little math mistakes like that. So 63 would be the equivalent in the world of decimal. Any major questions? Kind of fun to convert things back and forth, at least. Y'all might think I'm nuts, and I understand that. All right. Anyway, moving on. So how it works, basically. All right, so as I've already said, and as the video said, this is based on serial communication. All right. In this case, we are mainly using RS-485. Could we use RS-232? Technically, yes. All right, again, if we go off based on the video, they did say RS-232 was an option, as well as Ethernet is another option. Or you can do Modbus over Ethernet, obviously. It changes a few things, but it is a possibility. Okay. Anyway, but traditionally this is based on serial. So, just like serial communication, RS-232, zeros are positive and ones are negative, right? So they're showing you that up here, right? So you've got 0, 0, and then we got 1, 1, 1, and then 0, and then a 1, 1, and then 0, 0, and then a 1, and then a 0. And I also love that these are diagonal. Why are these diagonal, not perfectly straight up and down? Analog. And this is actually a digital signal. This is an on or off. All right, if we go back to the wonderful world of when we first started talking about serial weeks ago, all right, remember, it takes time to convert from one value to another, right? It's not an instantaneous change. We want it to be instantaneous, all right, but it's not instantaneous, all right? So because it's not instantaneous, it takes time. And the longer your wires are, remember what happens when you have 2 wires running right next to each other? They basically form a small what? Starts with a C. Oh. Stores energy. Capacitor. All right. So a capacitor is just 2 plates very close to each other, not touching, that creates an electrical charge right there, or stores electrical charge. That's why when you have longer runs of wire, we have to go to lower data rates, because it takes that longer run of wire, acts like a bigger capacitor. That means it takes longer for the signal to go from a 0 to a 1, or in this case, -5 to 5 volts. All right. So, but that's why we have these as diagonals. So, very important fact there. All right. So the first byte that we're going to transmit, and that will be the slave ID. All right. And if you remember, I told you that was up to 247. All right. Now, I also just got finished telling you guys a few minutes ago that we like to use all the bits, right? So if we're talking hexadecimal here, and we're talking two spots, that's 256 different combinations. Why is it only 247? Specialty bits, right? Like maybe a broadcast message, or this, or that, whatever. They want to reserve some for future proofing, maybe, or if, for, I said, broadcast messages that everyone's going to listen to, those types of things. So there is a reason, but it's, again, I don't have the exact reason. Like, oh, 250 is this, and 250, I don't have that list. But they are saving that for some. Also, we might need to limit the number of slave devices, because remember, if the master has to initiate communication with everybody, that takes a lot of time. So if it has to go through 0 through 247, when each one takes 10 milliseconds, like that's 2,470 milliseconds. That's almost 2.5 seconds. So that also could be part of the reasoning. Anyway, so the first byte is our slave ID, somewhere between up to 247. The second byte is our function codes. We will come back to those in a minute. All right. The data field that will be relating to those function codes, that will be a variable length. All right, but it is always going to be, I forget how many bits, like minimum. It's going to be like in sequence. It's like, okay, maybe, no, it's not. Never mind. Cross that. Ignore what I just said. All right, and the last thing is our CRC, our cyclic redundancy check. All right, and that is 2 bytes added to the end of every Modbus message for error detection. What do we do in the world of RS-232 for error detection? Starts with a P. Parity. All right. Now, if you remember how parity works, all right, parity counts the number of ones in a message and says, okay, I'm doing even parity. Okay, there's 7 ones. I need to be a 1 in my parity check, so that way there's an even number, so that way that's how the parity works. The problem with parity checking is it only tracks the 1s and 0s. It doesn't track if 2 things get flipped. All right? So it is only pseudo good. It's not a great system. All right? CRC, it does check for errors, like, okay, a bit got flipped. It also checks for that the numbers are in the right order. The bits are in the right order. So it adds a whole nother level of error checking. All right. Maybe next class we'll actually talk about how CRC works. All right, but we're not getting into that one today. So now, function codes. Here we've got all the function codes. Right? I really hate this order on the screen. I don't know why they're in this order. This is just the order that I always see them in. But I went and I flipped them around for us. So they're in numerical order for our function code. All right, so that's me. But anyway, so here we have 01 is a read. All right. So you're reading a discrete output coils. Right. 2 is reading discrete input contexts. 3 is reading analog output holding registers, and 4 is reading analog input registers. All right. Registers are just like the space that the analog input's stored in. All right. So 1 through 4 is all read. It's just whether it's discrete output or input or analog output input. Nothing too crazy going on there. All right. And again, so the data that we might have there would be how many bits does it want to read? Does it want 1 bit? Does it want 5 bits? Those types of things. Also, where's it starting? Is it starting at the beginning? Is it starting at the middle? Those types of things. So we've got a little bit of data going on there. All right. And I guess I should. Those are just those 2. Okay, cool. All right. Now 5 and 6. All right, are writing. 5 and 6 and 15 and 16. There we go. All right, so 5 and 6 write a single bit. All right, so writes 1 discrete output coil or analog output coil, analog output. 15 and 16 are multiple. All right, so again, same idea as the reading, but a little bit different. And then 7 and 8 are exception status and loopback. So the exception status, this is a short message requesting the status of 8 digital points within the slave device. Now, if I'm saying 8 digital points, do you guys think those are actual, like, real world points? They might not be. All right. And this will provide the status of the 8 predefined points of the slave. So this could be items such as the status of the battery, whether memory protect has been enabled, the status of the remote input-output racks connected to the system. So are they all functioning, or are there error codes? All right. So that's the exception status. The loopback, which would be 08. So this is the objects function code, is to test the operation of the communication system without affecting the memory tables of the slave device. So basically you're going, hey, are you there? And it's going, yes, I am. We're good to go, type of thing. Like making sure there is actual communication there. We don't actually care about like getting information off the device or anything like that. It's just, are you there? Yes, okay, kind of responding back. Again, just kind of make sure that that loop is actually working there. So, all right, so here we've got some examples for you guys. All right, and this is where we start getting a little confusing. I will 100% admit that to you. All right, so we have slave devices have 4 tables, and that's what we have over here on the right. All right, so as you can see, if it's an output, we have read and write capabilities. If it's an input, we only have read capabilities. Does that surprise any of you? Right, you can't tell an input what to do. I can't tell a button to be pressed. It doesn't work. Right, so if it's an input, you only can say, hey, what's your status? An output, I can say, hey, what are you set to? Are you on right now? Like, I just want to double check to make sure my code is correct, type of thing. We can request that, or we can say, hey, turn on. So we can do both of those things. All right. We have some example messages down here at the bottom. We'll come back to those in a minute. So we have a coil equals 1 bit. All right, so remember we talked about, or I briefly mentioned that with the analog. When I said a register, it's a place to store information. All right, well here it's telling you a register is 16 bits of information. All right, that's a lot of information actually. 16, 2 to the 16th, that's, I don't know if that is off the top of my head. I've got a calculator right here, I should quick calculate it. In decimal, that's 65,535 different possible combinations. Actually, 36, right? That's a very large number. You might only have an analog sensor hooked up to that that only takes advantage of 8 of those 16 bits. But we're going to send all 16 anyway. So anyway, so that's the difference between a coil, which you can see, again, our discretes are coils, and our analogs are registers. Simple as color. All right, so analogs are going to be registers, discretes, either inputs or outputs, are going to be coils. All right, so down here, I've got a nice little example message going back and forth. All right, so what are these first 2 bits? Or 2 numbers? Are they? Slave ID. First byte. So the 11 and the 11 are the slave ID. Notice that the slave sends back its own ID. Seems a little weird, right? But again, that's just like error checking, making sure the right device is responding to me. It's going, yes, I am ID number 11. Here is my response. All right. And next we have 01. What was this? All right, that would be the function code. So what are we doing? I'll go back once. 5, here we go. 01, in this case, is saying read discrete output coils. All right, so we're actually going to say, hey, I want to know information about your output coils. This 0013, all right, we haven't talked about that completely yet, but that is the data address of the first coil to read. All right, so on the output coils, it says we are reading output coils. This is our coil range from 00001 to 09999. All right, so we've got like 9,999 different coils that we can read. Just a few. All right. So 13 is saying we're going to start at 13. Now, it's not exactly saying that, right? What is this in? It's in hexadecimal. See, now we're getting really confusing. All right, so hexadecimal. So if we were to convert hexadecimal to decimal, 13, well, 1 would be instead of 1 times 16, that's 16 plus 3 times 1, so that'd be 19. All right, now, and here's where the really weird part to me comes in. We then have to offset it by 1. Why do we offset it by 1? Where do we start? Start at 1, we don't start at 0. That's why we have to offset it by 1. So 13 is 19, which is actually 20. Y'all confused yet? Exactly. All right. So again, we take 13, we convert to hexadecimal. That says, okay, that's equal to 19. And then we say, okay, now we have to add 1 to it because we're starting counting at 1, we're not starting counting at 0. All right. So a little bit weird, but that's what's going on. That then sends us 0025. Or sorry. So this is the total number of coils that we want to read. All right. What does that mean? How many coils do we want to read? Do we want to read 25? No, because we're still in the world of hexadecimal. All right. So 2 times 16, that would be 32. 5, 37. All right. So we would send 37. All right. And then the OE84 here. That is our CRC. That is our checking. So the master sent all that. So you've got ID, function block, function code, sorry. Start, bit, number, CRC. All right. And at the bottom, we still have ID. We still have our function code. Now we have 05. All right, this is the number of data bits to follow. Number of data bits. All right, so if we look, 1, 2, 3, 4, 5. Holy crap, it works! All right, so we're always sending and then sorry, it's the data bits, data bytes, not bits, right? We're sending 8 bits here. All right. All right, so now why did we need to send 5 data bytes? Well, we said we wanted to read 37 coils. All right. If we would say, okay, how many bits do we need to send 37? That answer would be 5. All right. So if we did 37 divided by 8, that would give us 4 point something. Can I send a portion of a byte? No, I send the whole byte. So we'd have to pad that out and say, okay, we're going to have to send 5. You always round that one up. All right. So now I need some space. Great place to do this. I should have done this on a second screen. That's okay. All right. So if we were to actually decode all of this, CD would equal. So if we actually just did the math, CD is 20. No, sorry, that's not what I mean. Sorry. Like CD is not 20. C is what? A is 10, B is 11, 12, C is 13. I'm like, 13 times 16 is not 20, so screw that one up. Anyway, when we're sending back the information that we've read off that, all right, do you guys remember about MSB and LSB? Right, it's which coils am I sending first? And this to me is really weird. All right, so this is coils number 27 to 20. And then, because again, remember, we're starting at 20, right? Right here. We're starting at 20. So there's 20 at the end, 27 at the beginning. Then this one would be 28 to 35. All right. So it's weird. I mean, we are kind of starting at 20, but we're not actually. We're actually sending 27 first and then going down to 20. All right. Then we're also going to have some space holders for coils 56 to 52 because this last one has extra space. We didn't use it all, right? Because we only said we're only sending what, 5 out of those 8. So we need 3 bits of space holding. So that last one will have 3 extra zeros in it. You think it would just be like you'd have to request it in whole bytes or something like that, make life a little easier, but no, you don't have to. All right, and then we have our redundancy check here. Yeah, we will come back to the whole MSB things in a minute. All right, so here it is, slightly different. Here's a different example. So we have still device 11, as you can see here. Our function now is 2, so instead of reading outputs, we're now going to read inputs. We are now reading, the first one to read is actually going to be input 1,000 or 10,197. Why is it now 10,000? And if we go back to our little table here, our inputs start at 10,000. You think it would be smart enough to know that, okay, I have, like, the receiver would just go, okay, I need to add 10,000 to whatever number they sent me. And that makes a lot more sense to me, but not how the system works. All right, so we'd send 10,197. Then we have the coils requested, so in this case, 22. And then we have our CRC again. And then down here again, you can see everything. So we're only having 22. So in this case, we're only sending 3 bytes back. So we have 3 bytes right there with 2 space holders. All right, and those 2 space holders are always at the beginning. All right, now, again, this to me is like the weird part. Because remember, the first input is actually this. So this is actually, one input. The requested read is 1, 2, 3, 4, 5, 6, 7, 8, and then it would be 9 through 16, and then 17 through 24. All right. So we're sending them, again, the whole MSB and LSB thing becomes a really big deal here. All right. And here's that example. So AE 41 versus 41 AE. Which one are we sending first? So you have to really know this. The Modbus spec doesn't define exactly how the data is stored in the registers. Therefore, some manufacturers implement Modbus equipment to store and transmit the higher byte first, followed by the lower byte, AE before 41. Others do it 41 before AE. Isn't that wonderful? Yeah, it should be part of the spec that, okay, you're going to send it this way. So that's something that you do need to go to be aware of. Do I have any notes on this page? Okay. We're good there. We're good there. All right. The order in the long one really doesn't matter. Whether you say AE 41 or 41 AE, it doesn't matter as long as what? Everyone knows which one's going to be first. Right? It doesn't matter if I tell you 41 then AE or AE before. As long as you and I both know that I'm sending the most significant bit first or the least significant. As long as you and I have this agreement, it's fine. All right. But could you imagine that screwing up your coding in your PLC? You're thinking you're getting, 0, 0, 1, 1, 0, 1, 0, 0, or 0, 1. And in fact, they're sending 1, 0, 1, 0, 1, 1, 0, 0. And you're like, yeah, this bit, I'm looking, when's this sensor going true in the real world? Like, you're like, there's a part in front of that sensor. You're like, why is the PLC thinking there's not a part in front of that sensor? And then you realize, oh, it's because this one, over here, not over there. Which either means in your code you have to be really backwards because you have to be like, I need sensor input 8 when you really need sensor input 1. It's just a matter of flip-flopping things if you can't figure out how to fix it. So technically you could like brute force this in a really bad situation. You have to leave like really heavy notes somewhere or why your code is funky. But technically you could just brute force it when you're in your PLC going, yeah, input 8 is what I need. But really you need input 1 or whatever, as long as you go with that. All right, so you do want to have a Modbus map, and this is just a list of individual slave devices. Some devices are built with a fixed map. So this is what it's going to be, and the manufacturer has defined that. Some allow you to define it. But you do want to be careful of what's going on. And what this map would say is, oh, this is a pressure device, or pressure sensor, or a temperature sensor, or a generic I/O, or something along those lines. Where the data is stored, so which tables and which data addresses, how we're storing it, data types, are we doing it by byte, are we doing it by word, are we, again, most significant, least significant, those types of things. So a lot of, again, flexibility going on there. All right, and the last thing related specifically to the wonderful world of Modbus is the extended register addresses. All right, so we could actually go have more data on there, really what it comes to. So the register is 40,000 to 49,999 correspond to data addresses. That's only 0000 to 270E. If we utilize the last remaining addresses from 270F to FFF, right, if we finish out the bytes, we have over 6 times as many registers that can be available to us. A lot more information. So we could do that. So we just got to be kind of careful about that. Some software will limit you to only $49.99. Some will allow you to extend into that. It's really kind of something that you need to be kind of careful of, what it comes down to. So as much as Modbus is open source and everybody should be able to use it and it should all just work, well, there's still not, everything's not defined. Again, most significant versus like, no, that should just be defined. And to me, it's like, well, these registers exist, right? We're using the bytes for them. We might as well just allow access to them. Why are we using those extra bits for information that we're not actually using? Might as well use them. As long as the device has space for it. The other question, memory. All right. And the other thing is, go back. Discard it. 12. There we go. Other thing we have is 2-byte slave addressing. All right. And again, this is going to be a modification to the protocol. This is not the standard protocol. This is protocol, I'm going to 2.1 or modify, whatever we're going to call it. That does allow for 2-byte slave address. All right. So that takes our 247 device max limit. All right. And that bumps it up to 65,535. All right. So just kind of something to be aware of. Like that could happen. Everything, both the master and all the slaves need to be able to handle this. And the reason is that screws with when you're sending information out. Right? If you're like, oh yeah, we're doing single byte, and it's expecting 1 byte for a slave address, like 11 or 52, and all of a sudden you're now sending 1212. And it's saying, oh, the first 2 are that's the address, the next 2 are, this information, right? The function code. All of a sudden now that information is all screwy. So everything, both the master and the slaves, have to be able to support the 2-byte addressing. Why would you need 65,000 different devices on your network? I have no freaking clue. Right? That one makes absolutely no sense. But maybe you do. Or maybe you just need like 255 devices. And you can't do it with the base one. So you're like, oh, we need a few more. Let's go 2 bytes. That's really what it comes down to. All right. By default, and simple Modbus software only uses 1-byte addressing. As soon as you go greater, it automatically will switch to 2-byte if your system, again, supports that capability. So something to be aware of. So, all right, that is really Modbus in a nutshell. Any questions for me? Okay. The biggest thing we kind of hit up, outside of Modbus today is the whole hexadecimal. How do we convert from A to B and B to A? Going back and forth the world of decimal. I made you guys do that a little bit with binary, right? So we got a little bit going on there. So we've not done binary, we've done hexadecimal. That basically covers all of the different number formats, I'll call it, that we're going to be probably focused on in this class. So it's really annoying having hexadecimal, especially when you look at it if you don't see any letters, right? If you don't see any letters and you don't recognize, oh, Modbus is hexadecimal, all of a sudden it's like, convert it, you're like, yeah, I need address 20, and like not working. How you're expecting, you're not getting the information you expect. But you have to remember, it's like, oh, that's hexadecimal. 20 is not actually 20. 20 is actually 32. All right, so 20 should be 1, 4. Off the top of my head, my math is working. All right. So something to keep in the back of your mind. Weird system, but it's just one that's going to be possibly dealing with it. And it's really not that bad once you get a little. So, any major questions? All right, that's the end of this video then.